All right, chemists, let's get started. Reminder that we have our review session tonight right after this class. Wish me luck. That's why I'm sitting, to get through it all. So the plan is to get through chapter 9 today. There's just a couple more slides going over, what to do with these orbital diagrams that we give you for the exam. It's not too bad from what I've heard from my other class, that it kind of all gets wrapped up on these last slides like a nice present. So the idea is we'll finish chapter 9 here, and we'll continue on if there will be time at the end here to start chapter 10. And so to remind you, our exam is just covering chapters 7 through 9. So even if we start chapter 10 today, that won't be assessed on the midterm. It will be on the final, though, because this class is like a freight train and we still have to keep going. With that in mind, we will finish chapter 9 today, so that means that homework will be due after the midterm. You guys have your midterm on Friday. Yes, very good. Okay, so we left off talking about our most advanced theory, molecular orbital theory. This theory not only considers the overlap of atomic orbitals, so back in valence bond theory, when we talk about sigma interactions, head-on overlap and side-by-side overlap to signify pi interactions, we also think about phasing, because these are waves. Molecular orbitals consider the wave nature of electrons. Waves can combine constructively to form bonding orbitals. So that's what you see here. The hardest interactions to understand are our p orbitals. We can have bonding orbitals that puts electron density between the atoms, but we can also have anti-bonding orbitals that essentially destroys the electron density between, within our bond, and puts electron density away from the atom. So we have bonding and anti-bonding. Anti-bonding is always higher in energy than our bonding orbital. But I want you to recognize that the atomic orbitals, how they're overlapping to give us our molecular orbitals, the atomic orbitals originate from a head-on overlap. So we still call it sigma, but now we add the designation, okay, is it bonding? So it's just like regular sigma, or is it anti-bonding, sigma star, right? So that's head-on overlap of two p orbitals that are on the same, the internuclear axis, versus, if you think about p orbitals, there's 3 different sets. There's 3 ml values. So our other interactions are our other p interactions on the other parts of the axes. So these interactions, if you look closely, are actually pi interactions. So here is one pi interaction, all right, along the x-axis, and then we have another pi interaction between 2 adjacent p orbitals along the y-axis. So these 2 bonding interactions are actually the same energy. These two 2p interactions, the bonding pi interactions, are the same energy. Same thing with the pi star interactions. They are actually the same energy. They're just aligned on different axes. And you actually can tell that these orbitals look the exact same. It's just like they're on different axes, all right? So these are our pi interactions. I always like to think they're always in sets of 2. So you can see that these 2 sets are our pi interactions. We just want to know that the pi star is higher in energy. And so again, the pi star, those pictures, has the electron density away from the atom bond right there, versus our bonding orbital has electron density between the atoms. Although it is above and below because it's a pi interaction, it still puts electron density between the atoms. So you see here in our anti-bonding interactions, you see this dotted line, which is trying to represent a node between the atoms themselves, where we essentially don't have electron density between the atoms. So those anti-bonding electrons or orbitals are higher in energy. So we see a splitting that looks something like this, where we have our sigma interactions on the top and bottom, and then our 2 sets of pi interactions in the middle here. So if you take account of all of the orbitals very carefully, if we have 2 atoms combining all of their p orbitals, how many orientations are in a p subshell? 3, right? Our MLs, or our orientations, it's -1, 0, +1, right? There's 3 orbitals. Remember, if you draw a p subshell, how many boxes do you draw? 3 boxes, yes. So if each atom has 3 boxes, how many boxes total are there? 6 boxes. So if we're combining 6 atomic orbitals, how many molecular orbitals do we get out? 6, yes, I don't want to make it too hard, all right? So that's what we see here. On the left and right, these are the 1, 2, 3, 4, 5, 6 atomic orbitals we're combining. Here in the middle, we are essentially rewriting the wave function of the molecule, solving the Schrodinger equation, and we're getting 6 new molecular orbitals out. And so the next part, when we do the electron filling, it's going to be a lot easier, but I want us to understand where these orbitals come from. Soon we're going to add electrons, and it'll get a lot easier of adding electrons. Because, like, let's think of it. If we had like 3 electrons coming from our atom, 3 different electrons in our p subshell, coming from our atom. There's a total of 6 electrons coming from our atom. So essentially how we would rewrite the electrons in our molecular orbital is we would put those 6 electrons in the center. We would redraw them following Hund's rule and Aufbau's principle. So all we would do is redraw the 6 electrons, but filling from the bottom top and following Hund's rule. So 1, 2, 3, 4, 5, 6. So that's kind of the last step here of MO theory, and we'll get there here in a little bit. I just want us to go over the ideas of what these orbitals look like and the concepts behind it. So let's. Oh yeah. So I think, did we talk about this? So here is putting it all together. Here are the S interactions and the P interactions that I talked about. So this chart you use for any diatomic, what I call the lighter 2p elements. So lithium all the way to diatomic nitrogen, you'll use this setup, this MO diagram where the molecular orbitals are in the middle. For the heavier second period elements, oxygen through diatomic neon, you'll use this ordering. Basically, the only difference is the ordering of the sigma and the pi, these ones in our p orbital interactions. It doesn't matter, okay? You don't have to memorize this. We give you the ordering. I just want you to recognize that there is a small difference between lighter period 2 elements and heavier ones. So all together, this is what you'll get on the exam, the ordering for the light period 2 elements and the heavy period 2 elements. And you see that the small difference is just the ordering of the sigma and the pi. So this is exactly what you'll get on the exam. I want you to be very aware of what we do give you and what we don't give you. And so that's the important thing here. And on this previous slide explains why there's a shift in sigma and pi, but that's not important. It's just because light elements tend to have p and s orbitals that mix a little bit, which causes a reordering of our molecular orbitals. But that's a small detail. Just know which graph to use when. And literally the graphs tell you, all right, that you'll use these orderings for these diatomics, and the heavier diatomics you'll use this ordering. So we give you this on the exam. I want you to know what interactions are shown, which ones aren't shown. So to kind of break apart these diagrams, the middle line, so note that they're not boxes here, they're lines just to make it a little bit cleaner, but we treat them the same as boxes. What kind of orbitals are shown in the middle here? These are what? These are our MOs, our molecular orbitals, versus what are the lines on the sides here? These are the atoms. So let's pretend I was talking about diatomic carbon. So the carbon atoms would go here. The carbon molecule would go in the center. So oftentimes what you do when putting this together is we're usually looking at valence electrons. So what's the electron configuration of carbon? It's 2s, 2p2, right? So we want to place those 4 electrons in our atomic orbitals. So this line, all right, this line represents our 2s. These 3 lines represent the 2p. So we can place those electrons, accordingly. So 1, 2, 3, 4. Just like we would in chapter 6, So those are atoms, and you'll draw the exact same thing on the other side because this is a diatomic, all right? So those are our atoms. But now in the middle, we want to think about the molecular orbitals that we get when we combine these certain orbitals. So think about s orbitals, all right? We have 2 spheres. What kind of interaction is that? Here, these 2. Sigma. So that's what is being shown in these molecular orbitals. One of them is sigma, the bonding orbital. What's the higher one? Sigma star, right? With that, you always have a bonding and an anti-bonding. Both of them are this interaction. It's just the phasing is different. Okay, what about our p interactions? Remember, we talked about 2 different kinds of p interactions. We can get the head-on overlap, just like our s orbitals, this kind. This kind of interaction is our sigma interaction, but which one of these lines is our sigma bonding interaction? This one? No, this one is the pi interaction. How do I know it's the pi interaction? It's a set of 2, yeah, so that's our pi bonding interaction. The next one is our sigma interaction. But then what is this set of 2? Is it pi as well? It is pi star, yes, it's pi star. And then the last one is sigma star, very good, all right. And then we can go over here and we think the exact same thing, all right? So label the molecular orbitals. So on the sides, we have our p atomic orbitals, our s atomic orbitals. But if we go down the middle lines, we have sigma, sigma star. What's next? What's this? Sigma star again? No, this one's sigma bonding because it's the lowest in energy within the p interaction. So it's sigma bonding, then it's pi bonding, then it's pi star, then it's sigma star. Okay, so I guess just memorize that. Memorize that. But know that, once you memorize one, for the other one, you just switch and make sure that you locate the appropriate, the 2 orbitals that represents the pi interaction. Okay. So that's what's shown. That's what's given on the exam. So note that these interactions are 2p and 2s. So these graphs are not, or these diagrams are not showing the 1s interactions. So keep that in mind. It's not showing the 1s interactions. But for heavy elements like this, it doesn't really matter because it's only valence electrons that are involved in bonding. So we don't need to really care about the inner core interactions, right? But if we did want to draw the 1s interactions, do we know what it would look like? It would look the same as this, it's just lower in energy. That's it. Okay, all right. So let's do some example problems. All right. If we combine these atomic orbitals, so each of these is a different interaction, what molecular orbital results? So I'll break it down to you in the simplest of terms. When thinking about molecular orbitals, again, the hardest of all of our theories, you want to think of 2 things. What kind of interaction, meaning what kind of overlap is taking place? Is it sigma or is it pi? Yeah, so what kind of interaction, what kind of overlap? Second, you want to think about, because now this is MO theory, electrons are not dots, they are waves. We want to think, okay, is the phasing in phase or out of phase? If it's in phase, we get constructive interference, we get a bonding orbital. If it's out of phase, if the combination of orbitals is out of phase, then we get an antibonding orbital. So those are the 2 things you want to think about. So first, what kind of interaction is that? Is that this or is that this? It's a pi interaction. Very good. How's the phasing? In phase. So is that bonding or anti-bonding? Bonding. Very good. All right. The next one. What is that? So bring these closer in your mind. Just bring them close together and think about what interaction's happening. Sigma. Yes. Sigma. Is it sigma regular or sigma star? Sigma regular. It's a bonding orbital. So see how that's interesting here? Both of these interactions are between p orbitals, but different interactions, way different interactions. Here, we're having a bonding orbital where electron density is going to be between the two atoms at sigma, and a pi interaction between p orbitals. The electron density will be above and below the atom, but it still strengthens the atom. All right, good. All right, pi, sigma. What about what interactions here? It's sigma again, but it just so happens to be between s orbitals. How's the phasing? It's out of phase. So this isn't a sigma, it's a sigma star. Yes. Okay. What about the next one? What's the next one? Pi star. What's the next one? Sigma star. See, it's not that bad. It's not that bad. Okay. Let's take it up a notch. Where would these molecular orbitals be on this diagram? So I'm going to number the molecular orbitals. I'm going to label it 1, 2, 3, 4, 5, 6. We already did the hard part. We already determined what kind of interactions are happening. We have pi, we have sigma star, we have pi star, and then we have sigma star. So we already figured out the overlap. Now we want to figure out where do they occur in the MO diagram. So we want to locate the, the interaction, but also you want to think about what atomic orbitals make up that interaction, because that will tell you whether it belongs in this top block between p interactions or this bottom block between s interactions. Because let's real quick, let's write in the molecular orbital names, designations for all of those molecular orbitals. So position 1 is what molecular orbital? What do we call that? Sigma. Then what's next? Sigma star. Then what's next? Sigma again. Then it's pi star, sigma star. So you might be noticing, wait, there are 2 sigmas on here. There are 2 sigma stars on here. How will I know where to place this one? You want to think what atomic orbitals make up this interaction. All right, so yes, this is a sigma star interaction, but which one is it? Is it this one, number 2, or is it number 6? It's number 6, because the interaction is between what atomic orbitals? P orbitals. So it has to be the interaction within, or the MO within P interactions. It can't be within this S interaction. So the last one here is 6. So which one is number 2 here? It would be this one, right? This is also a sigma interaction, but this one just so happens to be between S orbitals. So here is our number 2. Okay. Where will this interaction go? Will it go in 1 or will it go in 3? 3, yes. Well, both of them are sigma interactions. But this interaction is sigma between what atomic orbitals? P. Yeah, so it's going to be, what did I just say? 3. Okay. All right, what about this interaction? What number? What position? 4, yes, because there's only 1 pi spot for pi, and then there's only 1 spot for pi star, so just 5. There you go. Yay, we did it. Okay. Not so bad, right? Not so bad. Okay. But before we move on, so in these pictures, I show the atomic orbitals. There are other ways we can show, and so I didn't show the molecular orbitals. That's the thing, that these are the atomic orbitals combining, but recognize the molecular orbital that you get out looks a little bit different. So I want to actually show you what that looks like, so you're better equipped for the exam. Let me figure out. So I want to look at these examples here. So this is question 31 on one of my paper exams that I showed. So here's a bunch of different molecular orbitals, and I want you to tell me what position does this show up. All right, so, but the pictures here are a little bit different. See how I'm not showing the phasing? What I want you to see is, okay, is it a bonding orbital or is it an anti-bonding orbital? You also need to squint your eyes and think, okay, what atomic orbital is being combined here, right? It's the same kind of question. So first off, if we want to, what kind of interaction is this starred position? Sigma star, between what kind of atomic orbitals? P, yeah, between p orbitals. So that's what we're looking for. A sigma star, an anti-bonding orbital, so a head-on overlap interaction, but it has to be anti-bonding and it has to be between p orbitals. That's what we're looking for. There's a bunch of things here. There's a bunch of pictures, but I'll break it down for you. Let's look at this one. Let's look at B. What kind of, so remember, we're combining two atomic orbitals. If you squint your eyes, can you determine what two atomic orbitals are being combined here? Two different s orbitals. Is it bonding or anti-bonding? It's bonding because there's electron density between the atoms. That's why. All right, so this is a sigma regular, all right, interaction. It's a bonding interaction. Versus C, C is also between two s orbitals. But is there any electron density between the atoms themselves? So the black dots are the atoms. Is there any electron density there? No, there's not. So that's going to weaken the bond. So this is our sigma star interaction. See how both of them are between s orbitals? Both of them are head-on overlaps, but one puts electron density between the atoms. It's bonding. This one is anti-bonding. So these two orbitals will go here and here. These two, these are the sigma star between s orbitals. So let's actually locate this one because we're looking for a sigma star, but between p orbitals. So we want something that kind of looks like this, you know, puts electron density away from the atoms, but it has to be between p orbitals. So which one do we think it is? A, yeah, because if you squint real hard, and note, these are where the atom centers are. If you squint real hard, doesn't it look like two p orbitals are being combined? If you squint real hard, because you can see the little nodes on the other side. So these are two p atomic orbitals combining, but it puts electron density away from the bond itself. So this is sigma star between our two p interactions. So this A is the answer. A is the answer. Can you locate the bonding? Where's the sigma bonding orbital between p orbitals? E, yes, this is sigma between p orbitals because, again, if you squint your eyes, you can see the two p orbitals that are combining, and it puts electron density between the atoms, so it's bonding, so there's no star. All right, so here's another way that we can show it, all right? Okay. See, not so bad, right? Okay. All right, so let's go back. Where are we? All right, so there's that one. All right, so that one's this is a pretty tough question. All right, but you guys did good. So let's place electrons now. So let's place electrons. Let me go back up here real quick. So the idea is, you know, here's the diagram, the MO diagram. We need to place electrons. So the first rule for placing electrons is you want to identify what atoms are you combining. So I already showed the example for oxygen. Oxygen has 6 valence electrons, so 1, 2, 3, 4, 5, 6, but there's 2 oxygen atoms. So 1, 2, 3, 4, 5, 6. So how many total valence electrons do 2 oxygen atoms have? 12, yeah, 12. Just like Lewis structures, right? Count the total number of valence electrons. So basically what we're doing is taking these atomic orbitals, the electrons from atomic orbitals, rearranging them, replacing them in the center within our molecular orbitals. So we're going to rearrange those 12 electrons in the center here, following Aufbau's principle and Hund's rule. So we would do something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So just follow Aufbau's principle, Hund's rule. Just know how many electrons to place, and it came from valence electrons from the atoms themselves. So we can do that for all of the period 2 elements, and that's what's on this next slide. All right, that, you know, diatomic boron, 3 electrons on boron, so we're placing a total of 6 electrons, and so you see 6 electrons placed in the MOs. Carbon, you add 2 electrons, so there's a total of 8, and then nitrogen's 10, diatomic oxygen's 12, and so forth. So in this picture, I'm just showing you the MO part, like the middle. I'm only showing you the middle part, not the atom parts, just so we can see any trends that may arise. So the first thing we want to do when inspecting MO diagrams like this is the bond order. We can calculate bond order once you have an MO diagram. So here's my basic calculation for bond order specific for MO theory. It's number of electrons in bonding orbitals minus electrons in antibonding orbitals divided by 2. That's it. So if we look at boron, there's 1, 2, 3, 4 electrons in bonding orbitals minus how many electrons in antibonding? 2 divided by 2. So what's the bond order? 1. Good. Also a little trick here, because the sigma and sigma star are completely filled. It's 2 minus 2, so you can actually just ignore the bottom 2, and you can just look at what we call the frontier orbitals, the highest energy orbitals. So you can also do the calculation 2 over 2 equals 1. So you can do that as well. So that's the bond order for diatomic boron. What about diatomic carbon? What's the bond order? Same equation. How many bonding electrons? There's 4 bonding electrons, 0 antibonding, divided by 2. The bond order is 2. But let's think about it a little bit differently. To go from diatomic boron to diatomic carbon, don't we add 2 electrons? We added 2 electrons. Where did those 2 added electrons go? Can we locate them? Didn't we put them like here and here? Those 2 added electrons went into a bonding orbital. Adding electrons to bonding orbitals strengthens bond order, right? According to this equation, right? If we increase the number in bonding orbitals, it increases bond order. So that's consistent with what we know. Adding 2 electrons here in bonding orbitals will strengthen the bond. So we see the bond order go up from 1 to 2. Now, what is the bond order for diatomic nitrogen? 3, yes. So you can, do it a couple of ways. You can see, 6 electrons in bonding divided by 2 is 3. Or you can think, okay, if we compare carbon to nitrogen, we add another 2 electrons. Those added 2 electrons are in bonding orbitals. So we, again, strengthen the bond. We strengthen the bond. Okay, so without calculating it, let's look at diatomic oxygen. We add 2 more electrons. But what orbital are you adding it to? Antibonding. So what do you expect the bond order to do? Is it going to go up or is it going to go down? It's going to start to go down, right? Because we're weakening the bond now. We're putting electrons in antibonding orbitals, which are essentially bond-destroying orbitals. So, but if we calculated it, right, we're just looking at our 6 bonding electrons minus the 2 antibonding electrons over 2. The bond order for diatomic oxygen is 2. Is that consistent with what we know about oxygen, diatomic oxygen? Yes, it is. That's gross. What about diatomic nitrogen? Do we know what the Lewis structure for diatomic nitrogen is? Yeah, it's a triple bond, isn't it? And then for oxygen, it's a double bond. Yeah. So here's, showcasing that, MO theory is the most complicated. It's the most tedious, but it's the most correct. And it's correct with all of the rest of the theories, the simpler theories that we've discussed previously. It's just, I will give it to you. It's very tedious. All right. Lastly, diatomic fluorine. What is the bond order? 1. Is that consistent with what we know about diatomic fluorine? Yes, it is. It's a single bond. Okay. What about diatomic neon? What's the bond order? 0, yeah, because it's 3 bonding electrons, or sorry, 6 bonding, 6 anti-bonding, so it's 0. So the bond order is essentially, it's 0, that no bond is going to occur between 2 neon atoms. But that's consistent with what we know. Neon's a noble gas. It's never going to make a bond, right? So that's how we can ask questions with molecular orbital theory. It all relates to bond order, all right? That in order to understand or calculate bond order for these molecules, we need to draw out the full molecular orbital diagram. All right. Other questions we can ask are have to do with magnetism. So we can look at the full MO diagram and predict whether these substances will respond to a magnetic field or not. Paramagnetic substances are substances that just have unpaired electrons. You have to have at least one unpaired electron, at least one. Diamagnetic substances have everything paired. That's it. So, diatomic boron, is that predicted to be para or diamagnetic? Para, because there are unpaired electrons. What about diatomic carbon? Dia, because everything's paired. What about diatomic nitrogen? Dia, because everything's paired. What about diatomic oxygen? Para, because you have two unpaired right there. So if you use the wrong ordering, if you use the wrong, MO ordering diagram, you might get this question wrong, because note how the only way to get paramagnetic substances here is like using Hund's rule when we do the pi or pi star orbitals. All right. What about diatomic fluorine? Dia, because everything's paired. And then even though diatomic neon won't exist, it's still dia because everything's paired in its MO diagram. So both of these questions are really contingent with, can you draw the MO diagram for the neutral atom? And that's the hard part, right? So locating which MO ordering do I use, how many valence electrons do I place, follow Aufbau's principle and Hund's rule, and hopefully you know which ones are bonding, which ones are anti-bonding, so you can get bond order or predict magnetism. Okay, so let's get a little bit harder here. Okay, so let's move on to how we can ask exam questions, all right? So I'll show you the strategy on how we do this. So here's a question: which of these four substances are paramagnetic? So are we looking for paired electrons or unpaired electrons? Unpaired, yeah, so we're looking for unpaired electrons. Okay, so the strategy here is, well, there's two substances that are neutral, and those MO diagrams are already given, but we also give options for anions. So simply to draw the MO diagram for any of the anions, you start with the neutral compound and you just add electrons or remove electrons appropriately. So since N2 minus is an anion, we add 2 electrons. To compare oxygen and make it oxygen 2 minus, we also add 2 electrons to the MO diagram, and that's it. We add 2 electrons, but to the next available spot. So we need to follow our Aufbau's principle, Hund's rule, those things. So let's focus on nitrogen and oxygen. Okay, so nitrogen is what? Para or diamagnetic? Dia, because everything is paired. What about diatomic oxygen? Para, because we do have those 2 unpaired. So para, yes. So that's a D. That's a D for dia. So we have the neutral. So let's just add 2 electrons to the diagram to make the anion. So let's focus on nitrogen first. So where will the next 2 electrons go? Can I just put them anywhere? No, yeah, you put them in the pi star. So the first one goes there. Where's the next one go? And the next one, yes. So nitrogen anion is what? Paramagnetic, yes, it's paramagnetic. What about oxygen 2 minus? So we start with the neutral, we add 2 electrons, but where do they go? They go into pi star as well, but now they're spin down. So O2 anion is actually diamagnetic, all right? And of course, if we were trying to look at cations, we would just remove the highest energy electrons. All right, so that's another way we can ask questions, not only on the neutral atom, but the anion or cation as well. But all you have to do is just start with the neutral MO diagram and add or remove electrons as necessary. Okay, how else can I ask questions? All right, what molecule has a larger bond enthalpy? So I am essentially asking which of these pairs of substances is stronger. Which one has the stronger bond? So in these examples, I'm essentially asking you to calculate bond order. So what bond order am I looking for? Am I looking for the high one or the low one of the pair? You want to look for the higher bond order of the pair. That will tell you the stronger bond. Okay? So of all of these, they are, neutral diatomics, and we add electrons. So if this was like Lewis theory or like, Lewis structures, you may think, oh, well, yeah, if you add electrons to a bond, you'll strengthen the bond, right? But MO theory actually doesn't necessarily say that, because if you add 2 electrons to a bond, you don't know, is it going into a bonding orbital or an anti-bonding orbital? So there you can strengthen the bond or you can weaken the bond. So we actually have to draw out the whole MO diagram. So let's do that. So diatomic nitrogen, based upon its MO, what's its bond order? 3. We add 2 electrons, 1, 2. Do we weaken or strengthen the bond? Weaken, because it's in a pi star. It actually makes the bond order of 2. So the neutral diatomic nitrogen has the stronger bond because its bond order is higher. Okay. Oxygen and oxygen 2 minus. So the bond order in diatomic oxygen is 2. O2 2 minus, we add 2 electrons. We're adding those electrons in pi star. So we are essentially weakening the bond. Bond order goes to 1. So the neutral oxygen also has the stronger bond, because we're just looking for higher bond order. All right, last one. Carbon and carbon 2 minus. So bond order in diatomic carbon is 2. You agree with me? Yeah, 2. We add 2 electrons to this MO. What does the bond order become? 3, because the electrons that we're adding are going into a bonding orbital. So it's strengthening this bond order calculation. So our stronger bond is what? The neutral or the anion? Anion in this case. And again, it's because of thinking about where the added electrons are going. Is it going in a bonding orbital or an anti-bonding orbital? And that will, dictate whether you strengthen or weaken the bond. Right? So this question really is no different than this question. You have to draw the MO diagram and inspect it. So how else can we ask this question? Which molecule has the longer bond? So remember how bond length relates to bond order? So if we're looking for the longer bond, what molecule do we want to choose in terms of bond order? The smaller, lower bond order. That's the one that we're looking for. So unfortunately, for these pairs, we just need to calculate bond order for them in order to figure out which one has the longer bond. So let's do that. So bond order for diatomic boron is 1. The anion, we add 2 electrons to the diagram. So we add them to the next available spot. That makes the bond order for the anion become 2. So the neutral boron, because it has the lower bond order, has the longer bond. All right. What about fluorine, diatomic fluorine? As the neutral molecule, what's the bond order? How do we calculate it? 6 minus 4, 4 in anti-bonding. All right, I'll highlight it. So there's 6 electrons in bonding, 4 in anti-bonding. So 6 minus 4 over 2 is 1. So diatomic fluorine has a bond order of 1. And that's consistent with its Lewis structure. Okay, great. What if we make the cation? So we're not adding electrons now, we are removing them. But what electrons do we remove? Any of them? No, we remove the highest energy ones. So if we remove the highest energy electrons in diatomic fluorine, what kind of electrons are they? Anti-bonding electrons. So we're removing these electrons. Right? So do we strengthen or weaken the bond if we remove anti-bonding electrons? We actually strengthen the bond because essentially we are making this number, the number of electrons in anti-bonding, we're making this a smaller number. All right, and so we're subtracting a smaller number, so bond order actually goes up overall. So diatomic fluorine as the anion has a bond order of 2. All right, so it has a higher bond order, so it's the neutral molecule again that is the one we want. Okay, last one. Carbon and diatomic so diatomic carbon and the cation. So neutral carbon, bond order of 2. If we remove 2 electrons, we're removing what kind of electrons? Bonding. Do we weaken or strengthen the bond if we do that? We weaken it. So we are looking for the weaker bond is the longer bond, so it's C2+. In your head, I want you to recognize that the last 3 slides, they're all the same question. You just have to draw the Lewis structure, or draw the MO diagram, and inspect bond order, inspect the electrons in those molecular orbitals. Do we have another one? No, we don't. Okay, so that's it for placing electrons. So I just wanted to kind of take a deeper look at oxygen, the MO diagram for oxygen. Let's look at that real quick. Okay, when we calculate the bond order for oxygen, actually, let's do that down here. Let's draw the MO diagram for oxygen. So this, doing it from scratch, right? So here's the ordering for oxygen, diatomic oxygen. How many valence electrons does each oxygen atom have? 6, so 6 valence electrons. So 1, 2, 3, 4, 5, 6 for each atom. 1, 2, 3, 4, 5, 6. So we have a total of 12 valence electrons to replace in our MO diagram. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Good. So those are all 12 electrons, valence electrons for oxygen. So let's calculate bond order. What's the bond order? 2. Yeah, so again, couple ways to do it. You can count all the bonding electrons, so 1, 2, 3, 4, 5, 6 minus 4 antibonding electrons gives you 2, or you can just completely ignore the 2s shell because everything's completely filled. The 2 bonding, 2 antibonding, they just cancel each other out. So you can think, oh, it's 6 minus 2 over 2. It doesn't matter, you know. Either case, you get a bond order of 2. Is that bond order consistent with our Lewis structure? Yes, it is. When you draw our Lewis structure, you get a double bond. But if we talk about magnetism of oxygen based upon this MO diagram, what's the magnetism of diatomic oxygen? Is it diamagnetic or para? It's paramagnetic, meaning that there's unpaired electrons in the MO. Does the Lewis structure indicate anything about unpaired electrons? No, it looks like everything's paired. There's 4 pairs of lone pairs, you know, there's electron pairs in the bonds. The Lewis structure actually doesn't indicate anything about magnetism. So that's kind of the weakness of Lewis structures. And that MO theory can explain much, much, much more than the simpler theories we've learned. But the beauty is that it's still consistent with everything that we've learned previously. All right, so that's the strength of MO theory. All right, let's look at a different example, okay? So all of the previous examples and the diagrams that you're given as your supplemental information are diatomics where the atoms are the same. It's like O2, N2, F2. We can also give you MO diagrams for what we call heterodiatomic molecules, meaning that it's 2 different elements. So in this case, it's a carbon and an oxygen atom that we're combining. All right, so for these types of questions, we have to give you the ordering of the molecular orbitals, but you can still place the electrons. If we give you the diagram, you can still place the electrons, all right? And we can still answer questions about it. So how many valence electrons are in carbon? 4. So 1, 2, 3, 4. How many valence electrons on oxygen? 6. 1, 2, 3, 4, 5, or sorry, there we go. Well, I did it out of order. I did not follow Aufbau's principle, but there's 6. Okay, so total, how many total valence electrons are coming from carbon and oxygen? 10. So we need to just replace those 10 electrons in our MO diagram, starting at the bottom, making sure to follow Hund's rule where necessary. So let's do that. So the first electrons go into the sigma interaction. So I even have the orbitals labeled for you here. All right, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Beautiful. Okay. So I think the question that's posed here is, what's the bond order? So we placed the electrons. I gave you the orbital, MO orbital designations. You can also calculate bond order. Do we know the bond order? What is it? It's 3, yes, because it's these two cancel. So there's 6 bonding electrons right here divided by 2, and there's 0 antibonding. So 6 divided by 2 is a bond order of 3. Is that consistent with the Lewis structure of carbon monoxide? Yes, it is. So if you've drawn carbon monoxide, the Lewis structure, it is a triple bond. It looks like this. Gross. So our most advanced theory is consistent, again, showing you it's consistent with everything we've learned about thus far. And it's the hardest because, again, it's the wave nature. Because literally what you're doing is solving the Schrodinger equation. To prove it to you, here's just kind of this is just for fun, a more complex MO diagram. In all of our examples, we just did diatomic, so just 2 atoms. We just combined 2 atoms, okay? Linear, like in a linear fashion. When things are linear, the symmetry is nicer on us. So here is a much more complex MO diagram. This is for water. Water, a substance that we think is like the most simple thing ever, right? It's just H2O. But because of the symmetry, its MO diagram becomes really, really complex because it's of its bent structure. But not to just like show off or anything. I want you to look at the details here of this MO diagram. I want you to realize, look, they labeled the molecular orbitals in the center with what? What sign is that? What is that Greek letter? That's psi. When did we learn about psi? Chapter 6, when we learned about the Schrodinger equation and the wave function. Because I want you to recognize that when you write out the molecular orbitals, all right, and these interactions, you're literally solving the wave function of the molecule. And that's because MO theory finally considers the wave nature of electrons, that we have constructive and deconstructive interferences. So the molecular orbitals, because we have, bonding, antibonding, constructive, deconstructive, we need to label them appropriately with these wave function, psi designations, right? So that's kind of like putting it all together, okay? We've talked about the electron for like a month now, all right? So like chapter 6, 7, 8, 9, we've just been talking about the electron for so long. I love the electron, all right? So when students ask me, they're like, why'd you go to do a PhD? It's because I wasn't done learning about the electron, all right? And so that's what I studied in my graduate studies. So I wanted to show you my dissertation and prove to you that now you have enough foundational knowledge under your belt to understand what I did. I promise you. So remember the other day we talked about sigma interactions. Sigma is the Greek letter for S. When you bring 2 s orbitals together, what kind of interaction is that? Sigma. When you bring 2 p orbitals together, you get pi. Pi is the Greek letter for p. So if we think about the next atomic orbital, d, 2 d orbitals coming together is a delta interaction, and that's what I studied in my PhD. So I wanted to show you. So here's the title of my dissertation. It sounds really fancy, but you know everything here. Investigation. That's a fancy word for study. Okay? Of selected molecular and crystalline systems. Remember in chapter 2, we talked about 2 classes of naming, right? Molecules use one naming scheme. Molecules form covalent bonds. We can draw Lewis structures of them. All right, so I studied molecular compounds that like discrete compounds, covalent bonds. Also crystalline systems. Think about chapter 2 in naming. We named molecular compounds, but we also named ionic compounds. Do ions form discrete molecules? No, they form like extended crystalline networks. So I essentially studied molecules and salt, okay, in my PhD, using ultra fast, which is just another word for fast, really fast. It's times 10 to the negative. I studied things in the femtosecond regime. So that's times 10 to the negative 15 seconds. Okay, so butt ton of zeros. Okay, real fast. Time-resolved infrared spectroscopy, so IR, that's a type of light that we've talked about in chapter 6. So I essentially poked molecules with light, both molecules and salt with light, and I studied them. That's what I did. Okay, and I poked them and made their electrons do things, and then I took pictures of them on a fast time scale. So that's what I did, but I wanted to show you a figure from my my PhD, because you know this. So this is an MO diagram that I made for my dissertation, but I promise you know what's going on here. So what I want you to recognize is that I'm combining two metals together. All right, so instead of two, like oxygen and oxygen combining together, and like S and P orbitals combining together, instead think about two metals combining together, but I'm combining their D orbitals. So if we look, I made these paddle wheel complexes, so these are the two metal centers that I'm combining. I make a quadruple bond between the two metals, so if you look, squint your eyes, there's 4 lines there. It's quadruple bond. There's 8 electrons between these two metal centers. So let's look at the MO diagram and the atomic orbitals that are combining, but recognize that it's between D orbitals. But the designation, sigma, pi, all those things, it still applies. So let's look at this first one. Here's our two metal centers right there and there. What kind of overlap is that? Sigma. What is it called? It's a sigma bond, all right? It just so happens to be between D orbitals, no big deal. What about the phasing? Is it good? Yeah, it's bonding, right? The phasing's good, so it's sigma. What do you think sigma star would look like? Sigma star. The interaction is still the same, right? But the phasing is different, right? So instead of 2 gray lobes, sigma star looks like this. Sigma star looks like that. So it looks the exact same, it's just the phasing's a little bit different, okay? So let's look at the next interaction, because you know sigma, the pi interaction. So again, these are D orbitals, but think about bringing these two D orbitals close together. How are those lobes interacting with one another? They're interacting in a side-by-side fashion, right? Okay, what about the phasing? Does it match? Yes, it does. So that's why it's a pi interaction. Do you know how many pi interactions are there? There's actually 2 of them. There's 2 sets. There's one in this plane and there's one in this plane. And that's what's shown on this side. So there's one on this plane and one laying down. All right, and then the last interaction is our delta bond, and that's 2 d orbitals face to face. And again, if you look closely, you can see that the phasing is correct, that each lobe has the correct phasing, and so it's bonding in type. And then our anti-bonding just has the phasing a little bit differently. All right, so this diagram probably looked complex to begin with, or like at first glance, but I promise you know the interactions and the label designations that I give it using the foundational knowledge that that you have. Okay, good, yes. Yes. Purple. Yeah. So there's some it's purple because there's electrons. There's electrons in, whoops. Oh, come on. There's electrons in these orbitals. And so what would happen is that light would be absorbed into these pi star orbitals. We call them low-lying pi star orbitals. And so this absorption of light is what caused purple to be reflected back into our eyes. So red and blue. So this would absorb around green. So this line is about the green wavelength, the energy of green light. And so what our eyes see, because what we see is reflected, is the blue and the red. And so it looked purple. So that thing that you just drew on looks a lot like the N1, N2, and 3 kind of graph. Is that That's because it is. I told you I wasn't done learning about the electron, all right? And so, yes, it's the exact same. It's the exact same. Yep. Cool. And so if that electron goes up, it also comes back down, and what does it do? It emits light, yes. So then fluorescence or even phosphorescence can happen. Yeah. What's up? Not necessarily. There's some more chemistry behind it, so it's a little bit more complex than that. Yeah. So Good. All right. So we're done talking about the electron. So we're going to move on to chapter 10, unless anyone else has questions. Yeah. I don't know. Yeah, you can look up my dissertation. It's like 200 pages. It's somewhere in there. Yeah. Okay. Anything else? All right. Okay, so we're going to move on to chapter 10, gases. So outlook for the rest of, okay, so we just finished chapter 9, so homework is due on Sunday, but it's probably best to, do a little bit before the midterm on Friday. It's in your best interest to do that. And then Wednesday we'll devote solely to midterm review. All right. Okay. All right. So gases. So here with the next 3 chapters, we're going to do gases in this chapter, liquids in the next chapter, and solids in the last chapter. So we're kind of bringing together all the concepts we've learned before. So we want to keep those trends, our understanding of electrons in our back pocket for the next chapters, because we're taking all of these composition and structure information and applying it to what do we actually observe in terms of properties or measurable things when we inspect our samples in lab. So this all relates to composition and structure is what dictates chemical properties that we see. So in chapter 10 specifically, we'll bring out our calculators again, but there's not that many calculations in 11 and 12. We've already did the majority of the math of this chapter. So we'll look at characteristics, we'll go back to measurements of things, talk about the ideal gas law, lots of calculations there, and then we'll talk about kinetic molecular theory that essentially explains all of the phenomena that we see in previous sections. So let's use our intuition and think about what makes a gas versus our other phases of matter, liquids and solids. So in your mind, imagine what a gas looks like. Is it homogeneous or heterogeneous? Homogeneous, I hope so. I hope the air that I'm breathing is the same air that you're breathing because it's uniform in composition. Is a gas sample mostly empty space, or are the particles really packed together? Empty space, very good. With that in mind, is a gas sample rigid or easily compressed? Easily compressed, okay. Is there limited motion? So think about the particles in the sample. So although you can't see them, imagine what those particles would look like. Is there limited motion or unrestricted motion? Unrestricted motion, yeah, those particles are bouncing off the walls, bouncing off each other, bouncing off you, like billiard balls with completely elastic collisions. And then finally, with that idea of like how the particles have unrestricted motion, do those particles exhibit strong attractions or weak attractions towards one another? Yeah, that's a little tricky one. Think about it. Unrestricted motion. 2 particles, they collide and they have an elastic collision, meaning that all of the energy is transferred. So is there any attraction between the particles if there's a completely elastic collision? No, yeah, so there's very weak or no attractions between gas particles. Good? All right. So with that in mind, let's debunk some misconceptions of gases while we're here. Let's think about the phase change of turning liquid water to gaseous water, liquid to gas. So let's think about the particle view of what that looks like. So here's the particle view of H2O liquid. What would the particle view of H2O gas look like? So keep in mind what we said about what it, over here, like what it looks like. So A, B, C, or D? C, yes, because when I turn H2O liquid to a gas, what kind of change is happening? It's a physical change. So do I change the identity? Do I break any bonds? Do I make any bonds? No. So that's why A, B, and D are wrong, because those are actually chemical change. You have to break bonds, at least some of the bonds, to make these different diagrams. We want water, the identity of water, to stay the exact same. So literally when we take a liquid to make it a gas, we're just changing how far apart the particles are from one another. All right, so that's why C is our answer. The particles are just further apart, more open space. Okay, good. Yes. All right, because the misconception is sometimes students think that you boil water, that it's a chemical change and you get hydrogen and oxygen gas and that's flammable. That doesn't happen when you boil water. Okay, so let's think about some gases that we interact with on Earth in our everyday life. We think about like the air that we breathe is composed of gases, relatively low molecular weight molecules and elements. So like diatomic hydrogen or diatomic nitrogen, oxygen is mostly what our air is comprised of. So a lot of the elements, the non-metal elements, are actually gases. They exist in what I say on Earth, I mean standard temperature and pressure. So standard pressure is 1 atmosphere. That's the pressure on Earth. And standard temperature, like somewhere between like 0 degrees Celsius to room temperature, that's the conditions I'm talking about. Because if we were, you know, on Mars, then the common gases we interact with might be different substances. These substances might take on different states depending on what pressure and what temperature you're in. Yeah. You can do anything given enough energy. Yes, you can. We actually did. Remember the Born-Haber cycle? What was the first step of the Born-Haber cycle? Was sublimation of a metal. Yeah. Like money, given enough energy, you can do anything. Okay. All right, so other gases. But again, with that energy in mind, would you ever run into metal in the gas phase? No, you won't, because it's just not stable at this temperature and pressure. But if you go, I don't know, to some crazy planet with like a ton, like no pressure and tons of heat, then maybe metals can be in the gas form. Okay, so common monoatomic elements and diatomic elements here. The kind of the factor here, commonality between these substances, they have relatively low molecular weights. They're molecules. So what we'll see in chapter 11 is that these ideas, these low molecular weight molecules end up having very weak intermolecular forces, that these particles are not very attracted to one another. So they very commonly exist in the gas phase at earthly temperatures and pressures. So also these compounds, organic compounds, they are also commonly or relatively low molecular weight. They also are gases at room temperature. So yeah, the commonality here, most of these things are molecular covalent molecules. They form discrete molecules that are weakly attracted towards one another. So they easily become gases. So that's kind of the big idea here. All right. All right. So let's debunk some more misconceptions. Let's pretend we go to Party City. Is that still a thing? Is Party City still around? Okay, all right. Because Circuit City is no longer around. Yeah, Circuit City. It's like a Best Buy. It's gone now. All right, so Party City's still around. So let's pretend we're going there to get some balloons filled. We're going to get some helium balloons filled. So you pick a balloon, you give it to the attendant person. They fill it with helium. How does the volume of your balloon change? Don't think about it too hard. Does it increase, decrease, become unchanged? If the attendant fills the balloon with helium gas, it increases, yes. Don't think I'm trying to trick you yet. Yes, it increases. You blow air into a balloon, what happens? It gets bigger. Yes, the volume increases. Okay. Yes, I know I warned you. I said debunking misconceptions. That one is true. That one's, I hope, obvious. Okay. It's the next one. Yeah, increases. Okay. So we fill the balloon with helium, right? To make the volume increase. How does the mass of the balloon change? Talk to someone next to you. What do you think happens? What do you think happens? Okay, what do we think? Does the mass go up, down, or go unchanged? It goes up. Yes, it goes up. We are paying for helium atoms. Helium atoms weigh, like they have mass, right? We're filling the balloon with helium atoms, they have mass. So the mass of the balloon must go up because we're literally putting helium atoms in it. But do you understand where the misconception is? Because as humans, we know that helium balloons float, right? So the common misconception is that the student, and this is common, all right? Like half of the 4 p.m. class got it wrong too, all right? They think, oh, like the balloon floats, it has less mass. No, like the mass decreases. No, you're mistaking density with mass. We are adding particles into the balloon, so the mass has to go up. But what is also happening is that the density of the balloon when it's filled with helium is less dense than air, and so that's what creates the buoyancy. The difference in density, not mass. So we're still adding mass to the balloon. It's the difference in density. So here's the numbers to prove it. The density of air is about 1.3 grams per liter. The density of helium is a fraction of that. Cool? Okay. All right. So those are the misconceptions. We're adding atoms in there. We paid for those atoms, right? So the mass should go up a little bit, but it goes up nonetheless. All right. So let's talk about some measurements we can make of gases. So a term and measurement that we haven't talked about before is pressure. The SI unit for pressure is a Pascal. It's defined as a force per unit area. So force over area. So the SI unit for force is a Newton. So like think about your physics, like Newton, over a unit area. So the SI unit is meters squared. So it's a Newton per meter squared. And so 1 Newton per meter squared is a Pascal. That's the SI unit. Pascal isn't really used that much in the gas world, mainly because humans are selfish, and we typically talk about pressures in terms of atmospheres. Specifically, an atmosphere is an Earth atmosphere because we're selfish, and we think, our Earth is, number one. So anyway, and typically we think about gases and pressures in terms of atmosphere. So where pressure of our earthly atmosphere comes from is actually coming from the gas particles of the air that surround us. If I took a column of air above my head and collected all of the gas particles, nitrogen, oxygen, whatever, CO2, if I collected all the particles above my head all the way out to the stratosphere and like condensed it and weighed it on like a scale, it would weigh about 14.7 pounds. All of those particles, all right, like miles of air. If I condense it all out and weighed it, it's about 14.7 pounds. So that's 14 psi. Right, means pounds per square inch, and that is another unit of pressure. That's a common unit that you interact with also, in your vehicles, like your car pressure. Like actually, just today my car pressure light went off because it's kind of cold out. And we'll learn about that with gas laws and how different variables, temperature, volume, pressure, all relate to one another. So I would just memorize these pressure conversions. All right, 1 atm, 760 millimeters of mercury, which is also the same as a torr. Here, the weird number for Pascal, I showed you, is 101,325 Pascal. It's like some crazy number. Is an ATM, and 1 ATM, like our earthly atmosphere, is 14.7 psi. So that gives us all the conversions we need to make any pressure conversion we want. We can whip out our dimensional analysis again. So if we wanted to convert this torr to ATM, we want to use these two conversions. Right, 1 ATM is 760 torr. So 760, is that number going to go on the top or the bottom? Bottom, yeah, because it's 760 torr is the value there, and 1 ATM is up top, and then you see here, that's the answer. So we need to fly through these slides because we only have so many days left of the semester, believe it or not. So I have the answers there for you. I'll just set it up for you. So we can also convert ATM to kilopascal. So it's probably best to convert ATM to Pascal first. All right, so 1 ATM is equal to 101,325 Pascal, but we're not done. We want to get to kilopascal. So how many kilopascals are in a, or how many pascals are in a kilopascal? 1,000. So is the 1,000 going to go in the top or the bottom? Bottom, yes. 1,000 pascals is a kilopascal. I think boats, nautical things, use kilopascal, I think. And so that's the answer. The answer is 122 kilopascal, right? Okay. So if you think about pressures like atmospheric pressures, if you use your phone app, like the weather app on my phone, it's stupid. They don't use millimeters of mercury. They use inches of mercury. I know, it's gross. I'm pretty sure. Is it on there? I think I make you do the conversion in recitation. But literally, it's just like inches to millimeters. Okay, it's not, is it, what is it right now? What is it right now? It's 30.35 inches of mercury. And so that is related to our torr value, which is millimeters of mercury. It's the same unit, just, different length scale, right? So the idea of atmospheric pressure and how we measure it, I just looked it up on my phone. What is the atmospheric pressure right now? Sometimes, the weather people, they say, oh, we're in a high pressure system. We're in a low pressure system. Literally, they're comparing that to regular atmospheric pressure, which is 760 millimeters of mercury or torr. And so if we're in a high pressure system, it's over 760. If it's low pressure, we're below that. So how we actually measure atmospheric pressure is with something called a barometer. So the barometer in the lab, which you guys will no longer go to, at least for this class, you will in 1220. In the balance room, this is the barometer that you use to measure atmospheric pressure. So the idea here is the bulb. So there's this red liquid. Focus on the red liquid. The blue one's just a thermometer. But inside this bulb is a vacuum. And so remember where atmospheric pressure is coming from. It's coming from the particles in the air, right? So this end of the tube is open. And so the atmosphere is pushing down on this tube against no pressure coming from this vacuum. So essentially the atmospheric pressure equalizes the length of this tube. And that's how you measure atmospheric pressure. So where the whole 760 millimeters of mercury comes into play is the same idea. So this picture is basically the same as the red tube. We have a vacuum in here. Atmospheric pressure is pushing down on this pool of mercury. This vacuum is not exerting any force. But what is exerting force is the weight of this mercury inside the tube. So what's happening here is that the atmospheric pressure is equalizing the force being exerted by the mercury inside this tube. So when you set up this experiment and you have regular atmospheric pressure here, the tube length of mercury is about 760 millimeters. So like, 3/4 of a meter. So not too high. All right. So that's easy enough to work with when it's mercury. So the question is, well, why don't people use like water or something? Like, why don't you, like mercury's bad, right? Like, why don't they use water? If they wanted to use water, we need enough water to equalize the atmospheric pressure. In order to do that, the water height level has to be 30 something feet high, right? You would have to climb like 5 flights of stairs in order to read the barometer. Do you want to do that? No. So mercury is okay. Some of the best barometers out there are still made of mercury because of how sensitive it is, and we don't have to worry about huge lengths. All right. So that's the whole idea here. This picture, recognize that there's atmospheric pressure force being pushed on this pool, and it's equalizing with the weight of the mercury inside the tube. So if the pressure changes, the height of the tube changes as well to equalize that force, because that's what gases try to do. Gases are always trying to equalize their force, the force being exerted on the walls of this container, with the surrounding force. All right? Okay. So I still have class right now. So the gases exerting a force, equalizing force with the surroundings. So if there's a change in pressure on the outside, the gas on the inside of the balloon will respond to it, typically in terms of changing volume, temperature, or pressure. All right, so gas inside, equalize with the outside. So let's show a couple more minutes. Let's this will be like my second to last slide. So keep that in mind. Gases are always trying to equalize force with the outside. So I have two manometers set up. So a manometer is kind of like a barometer, but it measures the pressure of a gas sample. So we have mercury. Oh, thank you. Thank you. A manometer measures pressure of a gas of a sample, but it's the same idea. We have this open-end tube. Okay, so let's just look at A right now. We have an open-ended tube that's open to the atmosphere. Let's just pretend it's 760 torr, all right? And it's pushing down on the mercury tube. The gas is also exerting a pressure, right? So based upon this picture, is this gas exerting more pressure than 760 torr or less pressure? Who's winning right now, the gas or the atmosphere? The atmosphere is winning. So is the pressure of the gas more or less than 760? Less, yes. When I say who's winning, is it easier? Yes, it is. Okay, so what about this picture? Who's winning? The gas, yeah, if the gas is pressing down here and the atmosphere is pressing over here, all right, giving the force. In this example, who has the higher pressure, gas or atmosphere? The gas, very good, okay? So let's give it some numbers. Let's pretend the height of A is 1 centimeter. I'll just make something up. 1 centimeter, okay? Which is equal to how many millimeters? 10 millimeters. So if this height is 10 millimeters, what is the pressure of the gas? What's the pressure of the gas if this height is 10 millimeters? Is it 770 or is it 750? Yes, it is 750. Let's think about it. The pressure of the gas is 750. Okay, 750 millimeters of mercury, all right? We said the height of the mercury right here is also 10 millimeters. So if you add those pressures up, there's pressure coming from here, 750 millimeters plus 10 millimeters equals the pressure exerted by the atmosphere. So equals 760. So do you see how that happens? So let's do another example over here. Let's pretend this height is 5 centimeters. Okay, 5 centimeters, so 50 millimeters. What is the pressure of the gas of the sample? Do you add 50 or do you subtract 50? You add 50 in this case, yeah. So it would be, I guess, 810 millimeters of mercury. So the idea here is, okay, remember the gases are trying to equalize their force. So there's pressure of the atmosphere coming down here, that's 760, we're adding an additional 50 millimeters, and that is equal to the pressure of the gas on the other side. If you think about it in terms of like, you know, who's winning in this case. All right, and so yeah, the answer here would be 810. Which gas sample exerts a pressure greater than 1 atmosphere? So I think it's just B, based upon that. All right, so this is a good place to stop. On Monday, I will talk about the gas laws and do some demo stuff. Oh, wait, no, yes, Wednesday we have review. You have your exam on Friday. We have class on Monday. Yeah, this is a freight train. We're going, keep going.